esteemed speaker to the audience. Dr. Kumar obtained his UG and PG degrees from Chaudhry Charan Singh University, Uttar Pradesh. He completed his M.Tech in Solid State Materials and PhD in Physics from Indian Institute of Technology, Delhi in the year 2010. After this, he continued his postdoctoral research work from various internationally reputed institutions such as South Dakota State University, USA, and Colorado School of Mines and National Renewable Energy Laboratory, USA, etc. He joined the Indian Institute of Technology, Ropar as an assistant professor in physics in December 2013. He has also been associated with various international institutions as a visiting faculty. He has been working as an associate professor year 2019 onwards. Professor Kumar has a vast research experience, having more than 80 publications in various journals of high international repute. His research profile boasts of an H-index of 28, which is truly commendable. His name has been listed in the top 2% scientists globally by the Stanford University, USA. Apart from this, he has also been conferred upon by a number of national and international awards and recognitions. He has also been acting as a member of editorial boards for various journals of high international repute, such as Nano Express and Indian Journal of Pure and Applied Physics. We are truly honored to have you with us, sir. I would now like to invite Dr. Mukesh on the stage to kindly start with his talk and enlighten our audience. Dr. Mukesh, please.
Thank you very much for the kind introduction. So, in next 40-45 minutes, I will try to convey the message that the nanomaterials are really important, not only for research, but the products that we already have in the market. That's really commendable. So, topic of my research is 2D heterostructures, but don't go to the topic. I'll make sure as a teacher you will receive some message from the top. So these are the funding agencies that help us to establish the lab in IIT Ropar. So IIT Ropar funding, and then DST, DRDO, and all these funding agencies that help us to establish the lab. And I would like to thank the organizer. A special thanks to Vaishali Sharma as a chief patron, Dr. Ajay Sharma, advisor, Dr. Sanjeev Soni, convener of this, Dr. Neelu Mahajan, and organizing committee, especially Dr. Kirti Sharma. So these are the research that we are doing at IIT Ropar. So if you see that our research actually is mainly in four different areas. So we are working on flexible and transparent conducting oxides. That is one of the layer that is on your mobile phone that allows the light to out and then conduct the electricity simultaneously. So these materials has the properties of metal as well as insulator. Now other side we are working on 2D materials. So I'll tell you what is 2D materials and all these. Okay. So you can see actually that this image, so this is actually a vertically aligned 2D MOS2 that has a thickness of few nanometer. So that is like only 1 or 2 nanometer or 3 nanometer, and that is vertically about a 500 micron, and that is on very large area on 2 by 1 centimeter square, and you can use it for different application. Now we are also working on solar cell, but we have another speaker from NPL, so I hope he will discuss about that. And we are also working on other type of the photo detector that is funded from the Ministry of Defense. So that is, we are working on some kind of a special photo detector that sends some light that is not present on Earth atmosphere. So that's why actually it is known as solar blind photo detector. So I'll mainly actually discuss about this and then some part of that, but if the time permits, but most of the talk is mainly focused on basic. These are the facilities that we have in the lab. So that is actually is this the system that is use different physics to grow a layer of materials which has thickness from few nanometers to few hundreds of nanometer. So that is known as the combinatorial sputtering system. We have two of that, and then we have the in-house thermal chemical vapor deposition systems and all sort of characterization system that we have in the lab, and we have also another research facilities available. So that will actually presentation that how it will go. So I'll discuss about what is materials, what is nanomaterials. So the nanomaterials, when we are discussing about bulk material, so that is actually is anywhere starting from that depending on the application, but we generally call that 3D. So 3 actually is a number and capital D is degree of freedom. So that degree of freedom for the electrons. So when electron is not feeling any confinement, we are calling it as a 3D material. And the density of state is varying like this. Now if we suppose reduce one dimension, suppose I am moving on this floor, so I only have the 2 degree of freedom which I can go in x or y. But if I step down, that means I utilizing 3 degree of freedom, that is x, y and then height z. But if I confine myself to move only on this plane, on the dais, that means I have only 2 degree of freedom which is x and y. So if we restrict the motion of the electron in 2 dimension, then the degree of freedom, then the density of state will change. The density of state you can understand as the chairs that we have in this room. So that is the available position, and you consider yourself as an electron. So if you do not have any chair here, that means no student can sit here, right? So that means there is a gap between the band gap of the material semiconductor, that's why there is no electron there, and that is known as the band gap of the semiconductor. No electron is allowed to have that energy in the semiconductor because there is no density of state, right? Now if we have the 2D materials, that means one dimension is confined, then the density of state will change like this. Now if we are changing the density of state, that means we already change the arrangement of the chair in the room. Then the student will sit according to the presence of the chair. Now since the density of state is changed, so everything will change. The property of the material is changed. Now if we have the 1D, that means I can only walk in the line and nothing else. So that means if I am going in x direction, so only the 1 degree of freedom is allowed. So in that way the density of state will further change. And if I have the 0 degree of freedom, that means the electron is having confinement in x, y and z direction, right? And then the density of state will look like an artificial atom. So we have the states, vertical states, or the defined state like an atom. Now these are the things actually that if we have the free electron, it just give you an idea about that. If we have a free electron, then we consider that EK diagram, that means energy and momentum that electron can have inside the solid. Electron, if it is free, like in metal, so it can have all possible energies. But when this electron is placed inside a periodic arrangement of a lattice, then the magic start to happen. Then the electron will have the discontinuity, right? Discontinuity in the energy. This y scale is the energy and x scale is the k, which is nothing but the momentum. Then pi by a to minus pi by a, we will have the first thing, that is the first Brillouin zone. And how it comes? Because when the electron is moving, and we know that it is a de Broglie particle, it will have the wave. And when wave is propagating, then it will have the diffraction, right? So it's 2d sin theta is equal to n lambda. Whenever this condition will satisfy, electron will form the standing wave, and you know that the standing wave do not carry the energy, right? And this condition will satisfy whenever this k value will be pi by a, and that is demonstrated from here. When theta is 90, then you will see that the value of k is plus minus n pi by a, right? So that means the electron from here, like at this point, so these are the forbidden gap and these are the allowed gaps, right? And we already know that what is direct and indirect band gap. So that when the transition from the conduction band between conduction and valence band is happening at the same k values, that is there is no change in the momentum, then we are saying it is a direct band gap. And when it is happening at a different k values, then it need a momentum assistance from the phonon, right? So that is vibration, and then these materials generally do not emit light. And that is the reason actually silicon, although is a most studied element, but do not use in the light emitting diodes. Now when we are saying that nanomaterials, what things change? Why these materials are so important? Why we are discussing about that? That the reason actually these materials, when we are saying that the periodic table is kind of a puzzle, when we mix 2 or 3 elements, we can have a new material, right? So these materials are the having a different properties. So one we have, like suppose silicon, it is a semiconductor. If you have gold, it is a metal, and with a different color, different properties, melting temperature, all these are the fingerprint of these materials inside that. But can we imagine that if we change the size and these fundamental property will change? Yes, we can tune the properties of a material by changing the size. So that means the size is another dimensionality that we can change and tune the properties of the materials. What are these properties? Just listed the few properties like size dependent electrical properties. We can even consider a single electron transistor where only one electron goes from gate, from the source to drain, which is controlled by the capacitive gate. Or we can have this optical band gap. Suppose we have a semiconductor which band gap is about 2 electron volt. If you reduce the size, now the band gap will increase. So that means the size dependent optical properties. Because the conduction band, the bottom of the conduction band, that energy is no longer allowed to the electron. So there is always a 0 point energy. So the electron energy will start from little bit up from the bottom of the conduction band, and it is inversely proportional to the L square, which is the size of the material. Melting temperature. When we are saying that the gold, suppose having a melting temperature about 1000 degrees centigrade, but what about 5 nanometer diameter particle? What is the melting temperature of that? So melting temperature drastically reduce. Now we can also raise a question that how to determine the melting temperature of 5 nanometer? So that is again another question, right? So the melting temperature is no longer material property, but when you change the size, the melting temperature will drastically reduce. Now the magnetic properties, and all these actually property changes because the number of atoms present on the surface of this material drastically increases as we reducing the size. Now I'll just mention about the two important Nobel Prize. So that is actually 2023 Nobel Prize, that was on the quantum dots. So these are of same materials. If you reduce the size, the band gap will increase, and then if you shine with the UV light, they will emit a different colors. Or the old Nobel Prize, the 2010 Nobel Prize, that was a discovery of the new 2D materials, graphene. Now how we can make these materials? So these materials actually can be fabricated in lab very easily, but we can take two different approaches. One is top down. So if we have the bigger like material, so we can thin down and then we can go to the lower side, that is like lithography and all these techniques come into that. Or we can have the bottom up like Legos, we can arrange the atoms and then make the structure that we require. So let me give a little bit basic physics about that, how this material actually is being grown. So when we are growing these materials, so what we are doing from bottom up approach, we are creating the vapors of these atoms. So we are creating the vapors, and now we are condensing these vapors on the desired substrate, wherever, or the wafers where we want to grow these materials. How it is similar to the situation that is going to be happen in Punjab or northern part of that country, that foggy days and night, right? So we will have this fog. That means during the evening or the night, we will start to have lot of water vapors, and the temperature will drop down, and then we will have the situation where we will have this kind of things. So that means the amount of the water present in the ambient at that temperature is much more than it should be. So that actually this situation is like a supersaturation. Now when in the daytime, when the temperature rises, then this disappear. Water content is same, but the temperature increases, right? So when we have such situation, so that situation actually is like, we can define a supersaturation, which is S is equal to PV by PS minus 1, where PV is the vapor pressure of supersaturated vapors and PS is the vapor pressure above the solid at that temperature. So that means the amount of vapors present in the atmosphere is much more, right? We can create that situation, similar situation in lab. So we can evaporate some materials, and then that means the vapor pressure of that vapors is more at that particular temperature, and then we reduce little bit temperature when we transport these vapors, and we provide the substrate, and then they will condense. I just missed one point here, that when we have this kind of a situation, then under the trees actually we observe is kind of a rain like situation. Why it is so? Why there is no rain, other like no water? Because the sharp branches of this tree provides the condensation, the fast condensation. It reduces the condensation barrier. That's why these vapors condense, convert into the water, and then water droplet falls on the ground. So that is known as the heterogeneous nucleation. So vapors condenses, convert into the liquid, and then liquid actually falling on the ground. And this situation actually is homogeneous nucleation. The best example of homogeneous nucleation is rain. When we have clouds, right, and then we have rain, so they condenses themselves. And sometimes you have observed like there is no rain, and this time IIT Kanpur did some magic, and then we had a lot of rain, right? So that was a heterogeneous nucleation. They sprinkle something. Okay, so when we have this, so there is always change in the Gibbs free energy. So for what is the Gibbs free energy? So the Gibbs free actually you can understand that when the Gibbs free energy is negative, that means there is a spontaneous reaction. So there is a downhill reaction. So that means reactants are here, and then the final products are here. So if you have uphill reaction, that means the delta G is greater than 0. So that will tell you whether the reaction, thermodynamics will allow that reaction or not. And kinetics, what is the kinetics? Kinetics actually is the parameter we change to accelerate or deaccelerate the reaction. Okay, so what is that? So we have, this is the schematic of the system which is used to fabricate all these 2D structures. So this is a chemical vapor deposition. So we have, so this is the high temperature zone, and this is the material which is a solid. Then we increase the temperature, so that means we are creating the vapors. Now these vapors is being transported by using this carrier gas, and this is the substrate which is kept at a lower temperature. So these vapors will condense on this substrate, and then we will have the thin films or 2D materials growth by using this chemical vapor deposition. So this is the system that we have in the lab. So this is multi-target physical vapor deposition, the sputtering system, and this is actually a picture of the plasma. So I have one video, so let us see actually if it will play. So that was actually a video of the sputtering chamber, that is from the lab. So that was showing actually the formation of the plasma. So that we so let me actually see that. Okay, so that is actually is the creation of the plasma. So we have this solid target and we apply a high voltage between that, and then again actually creating the vapors which is going to be condensed on the substrate. Okay, so these are the things actually, again basic things when we are having like this, when these vapors are condensing on the substrate, in which direction they will grow. So that growth direction will be decided by the surface energy, and the surface energy actually for different planes, like suppose this is 100 plane, this is 110 plane, and this is 111 plane, and the surface energy of this actually is decided by this formula, which is NB is the broken bonds. Okay, so alpha actually, the epsilon is the bond strength, and Pa is the areal density, the atomic density on that particular plane. So you can see the number of atoms, the dangling bonds that is have, like it is a 4, so you can put all these, and the difference in the different these are the dangling bonds on different planes, and the density difference and all these actually leads to the surface energy difference. That's why even if you have the cubic system, and when the vapors are condensing on the substrate, they will start to grow in different direction. So different things actually is happened. So so these are the, like again 1D silicon nanowires. Okay, so that is being grown by using this chemical vapor deposition technique. So the what is happening actually, we have this metal catalyst, and then the vapors comes and then condense on this, and then these start to grow one-dimension nanostructures, the nanowires, and the catalyst actually is here, and that is actually plays a critical role for the condensation of these vapors at a higher rate. These are the in situ picture taken during the transmission electron microscopy. So these are the catalysts, okay, and then you can see this catalyst actually kept at a high temperature, and then it is condensing the vapors, and these vapors actually is condensing, and then it is forming the nanostructures of these material. Now these are the different photograph actually of this zero dimension system. So these are the zero dimension, like the nanoparticles that is grown. I grown actually this during my PhD time. So these are the nanowires or nanotubes. So you can see actually these beautiful nanowires that is going on the substrate, and these are the vertically aligned nanowires. So these are example of 1D structures. This is the example of 2D structure. So when we have, this is the substrate, and then this is the height of this layer. So so this and this is the scanning electron microscopy image that used to see the things, because these are at a nanoscale, we cannot see with our eyes, right? And so this is the things actually that looks from the top. Okay, now some part of that I thought actually I will discuss how to see at nanoscale. See, we can see with our eyes, and the visible sensitivity is from about 400 nanometer to 700 nanometer. Beyond, after 700 nanometer in NIR region or the UV region, we cannot see. And you know that with the eyes, or with the using the visible the light and the optical microscope, we can see with the resolution of lambda by 2. So if you use 400 nanometer, that means we cannot see less than 200 nanometer. But these things are of few nanometers. So how to see that? How do we know that this structure is 2 nanometer? Right? So you should ask the question to yourself and then try to find the answer. Okay. So how to see things? So we know that optical microscope has a limitation. And if something is in nanometer, how to see that? So one thing is possible, that we can utilize electron. I just mentioned that electron behaves like a wave, because if you accelerate that, it is a de Broglie wave, and the wavelength of that de Broglie wave you can control by accelerating that. If you are accelerating at high voltage, that means the wavelength will be shorter, and that wavelength you can utilize to imaging the different structure, even you can see a single atom. But these pictures is taken by the electron microscopy, like scanning electron microscopy or transmission electron microscopy, are of two dimension. Two dimension means like if you are taking a photograph in the camera, then the 3D picture is converted into 2D, right? And then within a color variation which gives a feeling that yes, it is a 3D picture. It's not a 3D, it is a 2D picture, right? So how we can take a 3D information about that material? So for that we utilize scanning probe microscopy. So what is that scanning probe microscopy? So in scanning probe microscopy we have the image like this. So these are the particles, right? And we have a color bar here which gives the information about the height. So this is very basic, you must have studied in your 12th or maybe BSc. So that scanning probe microscopy system works on a very basic principle, that is the force acting between the two atoms, right? So when we have the two atoms very far apart, then they will attract each other. If we bring them much closer, then they start to repel each other. And that famous potential actually is known as the Lennard-Joule potential, right? So when we have this atom very far, then they are attracting, and then this is the equilibrium distance, right? So this distance is like for iron, gold, nickel, all these have the fixed position. If you try to push them further, then we start to have the repulsion, very high repulsion. So by utilizing this, we are having this cantilever, okay, and that cantilever is like this atom at the end of this cantilever, and the atom of this sample will just feel that force, okay, and then whenever we have this change in the force, then we will have the image. So that is known as atomic force microscopy. Atomic means the force that is acting because of the atoms, the force we are sensing. Microscopy, any system that is imaging the picture of the system. So these are the different modes. So how it works? So these are the different modes of the system. Okay. So now there are few things. Okay. So now the tip actually is just like if you have just a mobile, okay, or any reflecting system. So what is happening? So you have the laser, because you need to see the deflection of this tip or cantilever. So how it is happening? If somebody from the audience is saying that my hand is very steady, please try, if you have the any reflecting surface, hold it like this, reflect the laser and just see at the top how steady hand you have. Okay. So what is happening is like you have the tip or the cantilever that is like this, and the laser actually shine at the back of this, and then whenever we are changing the force, so it is changing the reflection. So the situation is like this. You can see there. The laser actually. So you see that the laser, right? So whenever actually it is changing up and down, when the tip is changing, so the laser reflection will change, right? So the laser actually is now there, black, right? So when the tip actually is going up and down, the laser actually is shined from the back side, and then the reflection is there where we have a detector which is detecting the position and the intensity, which is known as the position sensitive photodetector. Okay. So how it is working? So the system actually look like this. So we have this is the piezo. This is the material actually when you apply the voltage, it changes the dimension, or vice versa as well. So and then this is the probe which is reflecting the laser, which is going to the position sensitive photodetector, and this feedback system actually going again to this. So this is actually is used to form the image. So this is the system look like. So I thought actually that will be helpful. So these are the different pictures of the system taken. Okay. So of atomic force microscopy, this is the picture of the position sensitive photodetector. So that the laser actually reflected from the back side of this cantilever, and then shining on this PSPD. So you see that the laser actually is here, shining here. Now if we insert this inside, so the laser will coincide here. Now whenever we are going on it has a 4 segment. So X, Y, so 1, 2, 3, 4. So whenever actually it is changing in vertical, so if you are going like this, so the position will change in 1 and 4. So whenever it's going up and down, so because based on that it will sense the force acting between the tip and sample, and then it will form the image of the particle. So this is how actually it works. So this is a laser which is reflected from there, and the force acting between this tip and the atom of the samples, and it is reflected here. Now it is correcting that. So there is a feedback system acting between them. So this is the about this piezo, how it works. Okay. So this is how actually is taking the picture. So that suppose actually it is at this position, okay, and the laser actually is shining. Now if it is going on the tip of that, so what will happen actually, it will bend, and that the laser reflection will go on this segment. Now this piezo will go back, and then to maintain at the center, so how much it goes back is equivalent to the height of this particle. So this is how it taking the image at the different location, and then okay. So these are the different force. So I'll just taken some images. So these are the you can see actually this is 1 micron, okay, and you can imagine actually what is the size of this nanoparticle, and what is the height of this nanoparticle, you can imagine from here. So this is the dark is the 0 and the bright is 30 nanometer. So this particle is about 30 nanometer height, and you can imagine actually most of the particle is about 15 nanometer height from the surface, and these are the dimension 1 micron by 1 micron. Okay, so these are the structures. Okay, now the difference between this scanning electron microscopy, transmission electron microscopy, and SPM is that the SCM and TEM provides 2D information, right? So if I have the finger like this, you can see actually it may be 1, right? Because the one, this one actually is hiding behind this, right? So there is no 3D information in SCM and TEM, but this SPM provides 3D information. So you can actually see that, you can measure the height of that or the distribution of the particles. There are different more advanced in that, so I am not going through that. So I would like to focus, the second part actually is the STM. So many people think that quantum mechanics, right? So quantum mechanics, Schrodinger equation, how many of you have solved that? Schrodinger equation, quantum mechanics, right? So when you have the potential barrier, the energy of the incident electron is less than the potential height, there is a finite probability that the electron will be found in the other side. That is known as the quantum tunneling. What is the application? The application is very beautiful, you can see that. You can observe that experimentally, okay? So this technique is based on the tunneling of the electron. So if you have the energy, okay, that is less than the energy of the barrier, the electron will tunnel on another side, and whatever the electron we are sending, and if you can detect how many electrons are going, it is nothing but the flow of current, right? So it's a very famous picture actually from this book. So this line from the left side is like having it is targeting to this man through this barrier. Man say that it's not possible for you to come on the other side, but the line says that, hey, I know quantum mechanics, so please run. Okay, so that is actually the basic physics, since you know that, so I am skipping. So this is the transmission probability, which is depending on minus 2k, and then d actually is this distance between this barrier. So the tip actually is like this, and when you have the air gap, the energy of the electron kept very small, so that the electron follow this tunneling behavior. The advantage of that is, like, if we change the distance between this tip and the sample means whatever we are taking the image, if it is changing by 1 angstrom, the current will change by 1 order of magnitude. So this technique is so powerful, it can image the distance between the two atoms, the gap between the two atoms. It can manipulate, it can take one atom and place at any other location. So this is how actually it works. So these are the different modes for that. So this is again actually for the student. So this STM is very powerful tool, and that is used for the calculation of this band gap and the density of a state of a material. How it is? So if you have the tip, so this is a tip and this is semiconductor, right? So yes, so this is the tip and this is semiconductor. Now if you have a semiconductor, we know that there is a band gap, and the band gap there is no state. So if there is no state, the electron cannot go and sit there, right? So it is just like if you have a water tank, on the one side the water level is up and then you have the gap. So whatever the water level up and down, the water cannot flow because there is no channel to flow the water. Unless until this water level on the left side goes up, then the water can go this side, right? Or if this level goes down, then the water can go from this to this side, right? So when we have the stiff, now you can imagine the conduction band states, valence band state, and the band gap. Not only that, if you dope a semiconductor with p-type or n-type conductivity, the dopants, you can calculate their activation energy, right? Because if you have any defects, right? If you have any defects, the electron can flow from here to here if you have any defects. So you can calculate the activation energy of that. So this is actually how you can calculate the band gap of a material, right? And this is how you can calculate the density, the activation energy of that. Okay, now here, do I have, how much time I have? Okay, so that's actually from here now the research work starts. Okay, so I kept that on just basic for that. So we are talking about 2D materials, but what is special about that? See, if you reduce any dimension, take a copy, right, and take one page, it's just like a 2D material. What is special about that? क्या ऐसा खास है इसमें? चारों तरफ शोर होता रहता है, नैनो नैनो नैनो, राइट? ऐसा नहीं हम काम कर रहे हैं इसलिए नैनो अच्छा है, नैनो वाकई में अच्छा है इसलिए हम काम कर रहे हैं, राइट? So the problem actually, for suppose you have a silicon bulk material, if you reduce the one dimension, bring it to the nanometer, these are also 2D materials. But what is special about these layered materials? If you thin down silicon, then you always have dangling bonds. Dangling bond means the bonds which is broken, unsaturated bonds, and then they saturate with the oxygen or water from the ambient. But in layered material, this is not the issue because there is no dangling bonds. It is just like the atoms within the layer is bound with the covalent bond, and out of the layer they are bound with the weak van der Waals forces. So you can peel them like a प्याज, okay? Onion की तरह layer by layer आप आराम से निकाल सकते हैं. And you don't need infrastructure to like sophisticated infrastructure. If you have the Scotch tape and 3D crystal of 2D materials, then by using a Scotch tape and a simple microscope, you can thin down to one monolayer. So these are the actually different. So this is the periodic table, and these are the all 2D materials. Now more than, actually if I am correct, more than 80 or 100 2D materials are available. So these materials actually do not have any dangling bonds out of the plane. That's why these materials are so important. Okay, so these are actually having a different band gap, starting from the graphene to hexagonal bond nitride. It's from 0 band gap to all the way to 6 electron volt, and you can make their heterostructures. And the beauty is that they do not have any dangling bonds, so there is no problem of the lattice mismatch. So they can go in any form, and then you can have the different heterostructures of that. Okay, so I'll just directly go to the some of the work actually. So these are the MOS2 that we have grown in the lab. So what is special about that? So these MOS2 actually, as you can see, is vertically aligned. So these MOS2 actually is vertically aligned. So that means, so with the normal MOS2 which is on the surface, so one side of this MOS2 actually is with the surface, so that you cannot utilize that. Now this is vertically aligned, you can use this surface and the edges as well. So we have utilized that, so we have grown on the large area and large number of varieties of the substrate you can grow. Now once you achieve that, now you, by using that, so on the wafer scale we optimize on 2-inch wafer, so you can have these structures. and you can utilize them for now different application depending on sensors, optical sensors and all this. Okay, so I'll just skip all this and then I'll just see actually, or we can have the hydrogen sensor, which is really important. I'll just go on the last. Okay. Okay. So this is actually just in the last what we are actually doing. So this is a special kind of photodetector. So our human eyes actually can see from 400 to 700 nanometer, but this photodetector can see 250 nanometer. So this 250 nanometer comes in the UVC region, which is absorbed by the ozone layer provided by Mother Nature. So that means there is no radiation 250 or less than that present on atmosphere. What is the disadvantage? This radiation causes the alteration of your DNA and the skin cancer. So that's why if we have the hole in the ozone layer, that's why this like is really bad, right? Why we are working on this material if there is no UVC radiation? So if we have this UVC radiation, a very small intensity present, which can be artificially present by using the missile or maybe fire or anything, we can easily detect. Now since there is no radiation present on this of this UVC radiation on Earth, this special photodetector is known as solar blind. So under intense sunlight, this photodetector is just like a dark. And this actually is better than the silicon photodetector that is specially working on UVC. Okay, so that is actually we are working on from UVC to all the way to NIR for defense application. So this is actually the summary. So it's growth of nanostructures and all this actually we have discussed. Okay, so we have a team of the dedicated students. I am just representing the research on their behalf. So many students actually graduated, 7 students graduated from the lab. Okay, and these are the master students. Thank you very much, and I'm happy to take a questions. Any question? Yeah, please.
Regarding the MS2 is shown by the SCM, the vertically aligned MS2. What is the delta K? I mean, how much layer there?
Okay, so the layer number of layer actually is 5 to 7. So that was confirmed by HRTEM.
So more than 5 layers is a, I mean, in principally it's not a confined state. It may be called as a 2D.
So 2D actually is a relative, like depending on what application we are using. Suppose we are saying that it is a direct band gap, so it is only like 1 or 2 layers when it is converting from the indirect to direct band gap because of the delta K, all this. But if you are talking about 5 to 7 layers, okay, so quantum confinement may not be there, but the main advantage that we utilize is a vertically aligned, and the both side of the surface actually is present for this absorption or this activation, and also on the edges. So that really good actually for the sensor fabrication, as a gas sensor as well as the light sensor. And you can have the different materials buried inside, like we observe for different p-type material that we grown is in between that, and that's really good actually efficiency.
You mean more surface area provided by
the vertical structure actually.
Because other thing is not going to provide, because it's like the 2D materials, its dangling bond is not present. So only the surface by volume ratio may be higher in case of these kind of the vertically aligned.
Yes, and the edges also, because we observe that the edges of these structures is having a lot of sulfur vacancies, and so if they are interconnected, if we control the density and if they are interconnected, they act like a connecting channels. So the resistance actually is very small.
So one more place in the C, because students are there. So
yeah.
One place you shown the Miller indices like 1.0.0. So what is the mean of that?
So this is 100 actually.
So because they will confuse, so that's why it's very important.
No. So that is 100. So this 100, 110 or 111.
Because 1.00 possible. Because if you see the 2D in 1D materials like A, B, C, A, so 4 indexing system like HK
in hexagonal
H
also.
plus K bar, but double dot is so that okay.
Yeah. Any question from the student side? No question? Yeah, please.
सर आपने बताया था कि नैनो स्केल पे मेल्टिंग पॉइंट कम हो जाता है बहुत ज़्यादा, तो फिर नैनो स्केल पे लाने के लिए उसको मतलब ज़्यादा वो लगता है मेहनत या फिर
Actually, when we are saying the melting temperature, okay, so all these properties are defined in the bulk. But if we reduce the size of this material, then it is observed that after particular size, the melting temperature start to reduce because of the large number of atom present on the surface. So the surface to volume ratio, the number of atom present on the surface and the number of atom present inside the bulk is drastically increased. So if these atoms are not tightly bounded, then if you increase the temperature, they will easy to lose, right? They will go apart and then it will show the liquid like properties.
तो फिर इसको एडवांटेज में नहीं यूज़ कर सकते.
And it is actually the property has changed, so you can use that. But again the question is, suppose you have 5 nanometer or 10 nanometer, right? So how you will see that? So you have to see by utilizing the HRTM, high resolution transmission electron microscopy, so that it is start to show the amorphous like structure. If it is crystalline, right, then how we will see that? So that is the fundamental property that start to change. Okay, and one more thing actually is like when you are having these nanomaterials, it is different size. Like it is not like if you are going 2 nanometer, then we will say quantum confinement. It is a different property, like mechanical property. It is a different size region. Electrical property, different size region, right? Optical property, different size region. Okay, no question? Okay, thank you.
So if there are no more questions, let's thank the speaker once again. I now request Dr. Neelu to kindly come on the dais and honor our esteemed speaker.